In this video, we'll explore some preliminary approaches to evaluating the quality of a regression model. We'll also review some Stat 155 concepts along the way. Let's start with a research goal. To improve their bike service, a bike share company wants to be able to predict the number of riders, Y, on a given day based on weather patterns such as wind speed and temperature, which we'll label as X1 and X2. In this relationship of interest, notice that our response variable or output variable of ridership is quantitative. This puts us in a regression setting, where we can model ridership Y by some function f of x1 and x2 plus the Greek letter epsilon. Here, the function f represents the structural relationship of Y with x1 and x2, whereas epsilon reflects the residual error. Mainly, this relationship isn't perfect. Now, the linear regression models that you studied in Stat 155 are a special case of this general model. In linear regression, we assume that the structure of this relationship can be written as a linear combination of the x variables, beta 0 plus beta 1 x1 plus beta 2 x2. Of course, the model here is merely theoretical. We don't actually know the value of these beta coefficients, but we can estimate them using sample data, a key theme in statistics and data science, estimation. We denote these estimates by putting hats on the beta coefficients and calling them beta hat. When we go ahead and estimate this model in R using our sample data, we get the following result. And the result might match your intuition. First, when controlling for temperature, we expect roughly 37 fewer riders for every 1 mile per hour increase in wind speed. People don't like riding in the wind. Further, when controlling for wind speed, we expect roughly 56 more riders for every 1 degree increase in temperature. We can then use this model to make predictions. For example, suppose it's a fairly cold 54 degrees Fahrenheit in Washington, D.C., with a wind speed of 16 miles per hour. Plugging these values into our sample model, the company could then predict that there will be roughly 2,389 riders. Since this is an estimate or prediction of Y, and not the actual observation, we denote it as Y hat. In reality, suppose there end up being 5,665 riders on that day, far more than our model predicted. Thus, the prediction error or residual on this day, obtained by subtracting the prediction Y hat from the observed Y value, is roughly 3,276. That is, we observed nearly 3,300 more riders than what the model predicted. Now, this is a good point to stop and reflect on the fact that we've been pretty careless. We built a model, we interpreted the model, and we applied this model without having any sense of whether or not it's a good model. And if it's not a good model, then there's a good chance that everything we just did is misleading. In this video, we'll explore 4 questions that we should ask about any model before using or reporting it. First, is our model simply wrong? That is, does it make reasonable assumptions about the relationship of interest? The picture on the left provides an example of a wrong model. Though the relationship is actually quadratic, the model assumes that it's linear. The model on the right is more reasonable. Now, as our models get more complicated and have more predictors, it becomes more difficult and sometimes even impossible to visualize the data and model in 2 dimensions, as we've done here. Thus, it becomes more difficult to determine whether our model assumptions are reasonable. Luckily, we have another tool, the residual plot. The residual plot plots the residuals on the y-axis versus the fitted values or predictions on the x-axis. And interpreting the plot here requires more art than science, or simply a lot of experience. So let's break down the residual plot for our bike model here. First, each dot corresponds to one observation or day in our data set. The dot up here, highlighted in yellow, represents the day for which we made a prediction earlier. On that cold and windy day, we predicted that there would be roughly 2,400 riders. That is its x-coordinate. However, the actual ridership ended up exceeding this prediction by roughly 3,300 riders, or the residual for this day was roughly 3,300, and we indicate this on the y-axis. Every dot above this horizontal line at 0 represents a similar situation. The number of riders we actually observed on that day exceeded the model prediction. In contrast, each dot below the 0 horizontal line represents a day on which we observed fewer riders than predicted. So, how can we use this plot to determine whether our model is wrong? The first thing to look for is whether the points are balanced above and below 0. Not just when we consider the plot as a whole, which is certainly the case that they're balanced above and below 0, but we're considering each little window across the entire span of the model. For example, in this window, the points appear to be balanced above and below 0. That is, our model is cutting through the center of the data, or actually capturing the appropriate relationship. This is roughly true across the entire span of the model. For example, we observe a similar balance as we move our window toward the area of the model that predicts higher ridership. So, in terms of being balanced above and below 0, this model looks pretty good. The next thing to look for in a residual plot is randomness. We want the points to appear random without any discernible trends. Again, assessing randomness just requires a lot of experience and is more art than science. And as somebody that does have a lot of experience, I examine the pattern here and think that, yeah, it looks pretty random. But I do see a couple of patterns that I might want to come back to and explore more detail later. First is the possible funnel or fan shape here. At the left side, the funnel is narrow. This demonstrates that where our model predictions are small, so where we're on the left side of the x-axis, our residuals also tend to be small. That is, they're close to 0. This means that the model accurately predicts when ridership is going to be low. For example, if it's really cold and really windy, the model probably accurately predicts that not many people will bike. However, the funnel then widens out as the predictions become larger. This means that our predictions of higher ridership, likely on less extreme days, are not as accurate. Putting that together, our model is great at predicting when ridership is going to be low, but the predictions on when ridership is going to be higher are a little bit more iffy. The funnel shape here indicates that our model might be heteroscedastic. Its accuracy decreases for days with higher ridership. But how much does this matter? Well, in cases of extreme heteroscedasticity, our model inference and prediction might be skewed, thus our model wrong. However, in cases of mild heteroscedasticity, as we have here, there's not much to worry about. Again, art versus science. You'll get the hang of it. A natural follow-up question of, is my model wrong, is it strong? The model at left is very strong. The data points are very close to the model trend, or the residuals are very small. Thus, X here is a strong predictor of Y. In contrast, in the model on the right, X is a weak predictor of Y. The residuals tend to be larger. Recall from Stat 155 that we can measure the model strength using R². The strong model on the left has an R² of 0.93, a value close to 1. The weak model on the right has an R-squared of 0.09, a value close to 0. R-squared has a nice interpretation. It measures the proportion of variability in y that's explained by the model. Thus, as a proportion, R-squared lives on the scale between 0 and 1. Consider the two extremes. If R-squared is 0, the model is terrible. It doesn't explain any variability in y. If R-squared is 1, the model is perfect. It perfectly explains all variability in y. The R-squared value for our bike model is somewhere in between, with an R-squared of 0.3104. Thus, our model only explains 31% of variability in ridership from day to day. The other 69% of the variability is left unexplained and might be accounted for by other factors that we didn't include in our analysis. For example, the time of day, the day of the week, events that might be happening around Washington, D.C., and so on. A third question to ask is whether our model produces accurate predictions. As with our other two questions, we can answer this by investigating the residuals. For example, the residuals in the left plot are very small. Thus, the predictions from this model tend to be very accurate. In contrast, the residuals in the right plot, represented by the red lines, are much larger. Thus, predictions calculated from this model will tend to be less accurate. Though this intuition is nice, we can more precisely measure the typical model prediction error using various metrics. Our first intuitive approach might be to calculate the average residual. That is, suppose we add the residual for the first observation to the residual for the second observation, and so on, all the way up to the residual for the nth observation, where n is our sample size. To then calculate the average residual, we divide this sum by sample size n. Now this turns out to be a bad idea. Notice in the plot here that the data points are balanced above and below the linear regression model. Thus, the corresponding residuals are balanced above and below 0. In other words, the positive residuals are canceled out by the negative residuals. Thus, if we simply sum up or average the residuals, we'll always get 0. Before moving on, let's define some shorthand notation that we'll be using throughout the semester. Instead of writing out the entire sum, as we did on the right side here, we can use the summation notation on the left. Here, we are summing the residual for all subjects I, where I goes from 1 to n. That is, we're adding up the residuals from subject 1 to subject n. Let's consider some better ideas. Instead of averaging the residuals, which cancel each other out, we can average the squared residuals, which are always positive and so can't cancel each other out. This measurement has an appropriate name. It's called the mean squared error, or MSE for short. Though MSE is a common measure of prediction accuracy, it has a drawback. Mainly, since it's dealing with squared residuals, its units are squared. Thus, MSE isn't very easy to interpret. But there's a simple solution. We can take a square root. Not surprisingly, the square root of the MSE is called the root mean squared error, or RMSE. Now, the square root puts this metric back on the original units. However, it also somewhat screws up the interpretation. The square root means that we can't technically interpret this as the average residual or error. So we end up with one more measure of prediction accuracy that's easier to interpret: the mean absolute error, or MAE. The MAE measures the average absolute value of the residuals. Thus, we can directly interpret MAE as the average or typical prediction error. Let's interpret these metrics for our bike model. First, the mean squared error indicates that the average squared prediction error is 1,676,379 riders squared, which is difficult to interpret. Taking the square root of the MSE, the root mean squared error is 1,295 riders. Though this isn't technically the average prediction error, we can say that it's the typical prediction error. Finally, the mean absolute error measures the average absolute prediction error. Here, we expect our model predictions to be off by 1,080 riders on average. Note that the ideas behind and the results of the MAE and our MSE metrics are similar. They're just two different approaches to measuring the typical prediction error. Finally, before moving on, notice that a natural follow-up question to these calculations is, are these prediction errors big or small? Answering that question requires some context. What are the implications of a bad prediction in our particular context? What's the scale of the y variable in the first place? So is being off by 1,000 riders on that grander scale of things, is that big or small? So leave those follow-up questions to class. A fourth and final question to ask ourselves when evaluating a model is it fair? Unlike the previous three questions, the answer is context dependent and not cut and dry. It depends upon many factors. For example, we need to understand who collected the data or who funded the data collection, how the data were collected, and the motivations behind the data collection. Further, it's important that we understand the potential implications of our analysis, ethical or otherwise. In our bike share analysis, the model we constructed is likely fair. The data were collected by the company in order to better anticipate and prepare for daily operations. The analysis is therefore unlikely to harm any customers or have any unethical consequences. That said, we might want to dig in further. For example, we might ask whether the privacy of customers was preserved in the data collection process. In conclusion, we've examined 4 questions to ask when evaluating our models. We'll get more practice implementing and examining these questions in practice during class.